Hello, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. So we were talking about a system and we are talking about the unknown quantities as well as the specified quantities. So we started with a simple system, 4-bus system. Please note all these buses are three-phase bus, and we said that let's say that bus 1 has got a generator, bus 2 also has got a generator, G1, G2, G1, G2, and bus 3 and bus 4 has got loads, and we said that bus 3 and bus 4 individual phases has got loads and we know their values. And but then at bus 2 there is a generator. I know that what is the total generation, say for example 170, and that total generation would be equal to the sum total of the generation of from phase A, phase B, phase C. But then we really cannot pre-specify the individual generation from individual phase. Just to understand this in a bit more clarity, let us just talk about a very simple system where I have got only one single generator G, and then it has got phase A, phase B, phase C, and then there is now some transmission line, line, transmission line, and then at the end of the transmission line there is phase A, phase B, phase C. So this is phase A, phase B, phase C. Now from phase A, so phase A, phase B, phase C, from phase C there is some load. I can really pre-specify, say PLC plus JQLC. Then I can also pre-specify, let's say some load here PLB plus JQLB, that I can again pre-specify. From here also I can pre-specify that what is the load here, individual load PLA plus JQLA, because these individual loads are connected, let's say in a kind of star fashion. Now to supply this, there will be some power here, there will be some power here, there will be some power here, and the total power out of the generator would be equal to this power, this plus this plus this, as well as the essentially the real power loss, and also the total reactive power generation by the generator comprising of all these three phases would be QLA plus QLB plus QLC plus any reactive power loss in the line. So then therefore, although we can pre-specify the load power at individual phase individually, but we really cannot pre-specify that ultimately how much power would be generated by phase A and how much power would be generated by phase B and how much power would be generated by phase C. But we can basically say that this generator is generating say 100 megawatt, but that is equal to the sum total of the generation from phase A plus phase B plus phase C. So here now again let us come back to this. So then therefore now here my total load is 250. So then obviously in this entire system the this generator will have to actually supply 80 megawatt plus P loss that it has to supply. But because we do not know what is the amount of loss, so then therefore I really cannot pre-specify what would be the total generation from G1. So then therefore for one generator we really cannot pre-specify any real power generation. So if I say that this is the slack, so then therefore for slack generation, or rather for the slack bus, we really cannot pre-specify any real power generation. So then therefore if there are m generators, so if there are m generators in the system, so for m generators in the system, for m generators in the system, right? Total real power generation can be pre-specified for m minus 1 generators only, right? For the remaining generator, which we also call the slack generator, remaining we which we also call the slack generator, the real power generation can be calculated after the load flow is solved, right? So then therefore this is my first set of pre-specified quantity. So that means I do have, so then therefore if I have got m generators, for example here in this case I have got 2 generators, so m is equal to 2. So out of this, so then here in this case my m is equal to 2. So then out of these 2 generators, m minus 1, that is equal to 1 for one generator, I have been able to pre-specify that what is the total amount of generation, say 170 megawatt, but what would be the loss, that I do not know. So as a result I also do not know what would be the actual generation by generator 1, that I can only calculate after the load flow is solved, that is that I can simply calculate only after I know all the bus voltages of the system. Now here another point, now here we said earlier that, I mean what are the, in this particular case, what are my system, I mean basically what are my quantities of interest. So in this 4 bus system my quantities of interest are, it appears, so in this 4 bus system, in the 4 bus system, quantities of interest quantities to be solved are VIP and theta IP. I is equal to 1 2 4, P is equal to A B C. Now if we recall our single phase load flow, what we used to say, we used to say that out of these 2 generators, usually except the slack generator, for all the other generators bus voltage magnitude is known, and also for the slack generator the bus voltage magnitude is known. So then therefore for the single phase case I would have said that my V1 and V2 are known. For single phase, for single phase case, for single phase case V1 and V2 are known, are known. But for 3 phase case, these 3 voltages can be totally unbalanced. That means V1A may not be equal to V1B, may not be equal to V1C. But for therefore, but for three phase case, I really cannot pre-specify what is V1A, what is V1B, V1C, and neither I can assume that that this generator terminal voltage will be always balanced. For example, here, I mean, let us again come back to this very simple generation and load. In this case, because these loads are unbalanced, if this PLA, PLB, if PLA is not equal to PLB, is not equal to PLC, as well as if QLA not equal to QLB, not equal to QLC, so then therefore these loads are unbalanced. Because these loads are unbalanced, so then therefore these currents IA, IB and IC, they will also be unbalanced. Because these are unbalanced, so then therefore because of this flow of this unbalanced current through this transmission line, the drop in the transmission line will also be unbalanced. So then therefore I can write here that this drop is also, voltage drop is unbalanced. Drop is unbalanced. Unbalanced means that they are not same in magnitude and angle. So voltage drop is unbalanced. Because this voltage drop is unbalanced, so then therefore this terminal voltage we also cannot expect to be balanced. But then for a generator, what it does internally it generates, and so then therefore these are basically the terminal buses. So these are basically the terminal buses, right? But for a generator, internally it generates an balanced voltage. So then therefore this two bus system we can represent it by this. So then therefore let us say that this is my terminal bus, this is the generator terminal bus, and then I have got transmission line. So this system we are now writing like this. So then transmission line. So this is my generator terminal bus, this one, this blue colored. So this is also, so let us say this is GTB. So this is my generator terminal bus GTB, and after that I have got load bus. So this is my load bus, load bus. So these are load bus my, so these three are load bus. So load bus LB. So these three are LB, and then I have got unbalanced load here, unbalanced load. Now because of the unbalanced load, the currents here would be unbalanced. So then this drop would be unbalanced, and then internally there will be one internal bus which is balanced, and between this internal bus and the terminal bus there is generator impedance. So this is generator impedance. So this is the generator internal bus. So GIB stands for generator internal bus, which is balanced, right? So then therefore what happens actually, internally every generator generates some balanced voltage, but because an unbalanced load is connected from its terminal, So then therefore unbalanced current flows out of the generator wires, or rather the generator phases, or rather the generator windings. Because of the flow of this unbalanced current through the generator winding, so this unbalanced current creates a drop inside the generator impedance. Because of this unbalanced drop, and as these currents are unbalanced, so then therefore the drop across the generator internal impedance, this is called generator internal impedance. So this is called, I can say that this is actually generator internal impedance, GII. I can say that this is generator internal impedance. Generator internal impedance. So GII stands for generator internal impedance. So what happens inside the generator? Generator generates a balanced voltage. So at GIB, that is at generator internal bus, generator generates a balanced voltage. Now this generator is essentially supplying an unbalanced load. Because of this unbalanced load, unbalanced current will flow. When this unbalanced current flows through this generator internal impedance, this will cause an unbalanced drop. Because this will cause an unbalanced drop, so then therefore even though the voltages at the generator internal impedance are balanced, but the generator terminal bus voltages would be unbalanced. So then therefore GTB, that is the generator terminal bus voltages, would be unbalanced. So then therefore we need to understand that GIB voltages are balanced. GIB voltages are balanced, that we need to understand, but generator terminal bus voltages are unbalanced. Let me underline them. GTB voltages are unbalanced, but GIB voltages are balanced. Correct. So generator internal bus voltages would be balanced because every generator generates an balanced voltage inside its winding. So internal bus and that one, please note, we do not have any physical access to this internal bus. It is just an kind of mathematical construction. I mean, this is kind of, let's say, a pseudo bus, which you imagine that essentially there is some bus, right? This is basically kind of, let's say, we can say that this is a virtual bus kind of a thing. We do not have any physical access to this, but we know that these voltages which is being generated internally by the generator, that is balanced, and to represent that generated balanced voltage, we do imagine that there is a bus inside the generator somewhere. It is a virtual bus. I mean, there is no physical existence of this bus. So generator internal bus voltages are balanced. That generator internal bus is connected to the generator terminal bus through the generator internal impedance, which is basically contributed by the generator zero sequence, positive sequence, as well as the negative sequence impedances. Now, when this unbalanced current drawn by the load is drawn from the generator, so this unbalanced current causes an unbalanced drop across the generator internal impedance. Because of this unbalanced drop across the generator internal impedance, the generator terminal bus voltages are also unbalanced, and of course the load bus voltages also will be unbalanced. So then therefore what happens for this two bus system? The load bus remains the same, but this generator, every generator is actually represented by two set of buses. One is the actual terminal bus and another is the generator internal bus. The actual terminal bus voltage, which has got its own physical existence, please note that the generator terminal bus has got its own physical existence. This generator terminal bus voltage would be unbalanced due to the fact that unbalanced load current would be drawn from the generator. But the generator internal bus, which is basically a virtual bus which does not have any physical existence. This is just our kind of assumption. So, but the voltage at this generator internal bus would be balanced because this voltage is actually generated by the generator winding arrangements. So then therefore generator internal bus, although it is a virtual bus, but for the sake of our calculation we will assume that this generator has got one internal bus. Every generator has got one internal bus. So then therefore that generator internal bus would be balanced, correct, and this internal bus would be connected to the generator terminal bus through its generator internal impedance, and that generator internal impedance would be contributed by the generator zero sequence, positive sequence and negative sequence reactance. So then every generator would be represented by actually two buses. So then therefore if we look at this four bus system, and now if we do represent every generator by its corresponding terminal bus as well as the internal bus, so then this system will look like this. So we have our initial bus 1, then bus 3, then bus 2, then bus 4. So bus 1, so this is bus 1, bus 2, bus 3, bus 4. So this is the initial condition. Now I have got an internal bus. So now this has got an internal bus. So this is an internal bus, and in between there is an impedance. So I call it bus 5, and here just to denote that now this generator is connected, and here this is the generator. Say I just a minute, let us say that this is bus 5, and this has got generator internal impedance, and this is bus 6, and now I have got a generator here. So now what happens? Bus 3 and bus 4 are the load bus. So I say that bus 3 and 4 they are load bus. Bus 1 and 2 they are generator terminal bus, and bus 5 and 6 generator internal bus. And this one, and of course please note that all these lines would be represented by their equivalent pi model, etc., so all these are known. This one is the generator internal impedance of generator 1. What is GII? That we have already defined in the last slide. GIA is called generator internal impedance, and this one is the GII of generator 2. Please note these impedances are also 3 cross 3 matrix. How this 3 cross 3 matrix would be computed, that we will discuss a little later on. But these are also can be represented by an equivalent 3 cross 3 matrix. It is basically, we if we know this zero sequence, positive sequence and negative sequence impedance. So from that zero sequence, positive sequence and negative sequence impedance, we can calculate back by the simple transformation the impedances in the phase ABC domains. Now, if we put this positive sequence, negative sequence and the zero sequence impedances at the diagonals of a 3 cross 3 matrix, and then if we apply the standard transformation matrices, then I actually get the final 3 cross 3 impedance matrix in the phase ABC domain, which is very standard thing. So, I mean, it is hopefully known to everybody, but if not, we will again discuss. But then basically, I mean, right now, let us just assume that this 3 cross 3 generator internal impedances are known. So, you see, originally there are 4 buses system, right? So, originally there are 4 buses in the system, but now this system has now been augmented into 6 buses. Now, here in this case, what we say is that the total number of bus here in this case, total number of bus is n is 4, and because there are 2 generators, m is 2, right. So, n is 4, m is 2, n is the number of generators. So, we write that n is the number of generator, n is the number of bus, sorry, n is the number of bus in the system, and m is the number of generator. Number of generators in the system. So, when we have got n buses and m generators, now that system is now augmented into 6 bus system. So, an n bus system, so here an n bus system is augmented to an n plus m bus system. Where are these? I mean, what are these extra m buses? These extra m buses are nothing but the internal buses for each and every generators in the system is augmented to an n plus n bus system because of the consideration of generator internal bus for every generator. So, then therefore, if there are m generators, we have to consider m internal buses. So, as a result, so m extra buses would be added. So, then therefore, now my bus, so essentially now my system size would be increased from n to n plus m. So, for example, here my system size earlier was 4, but now it has increased to 6. Out of this 6 buses, bus 1, 2, 3, 4, that is the original buses are unbalanced bus, but bus 5 and 6 are balanced bus. So then original, we also write down that original n buses. For example, here 1, 2, 3, 4, because these are terminal buses, the load buses, they will be unbalanced bus. So original n buses are unbalanced bus, and the internal m buses are balanced. Balanced buses means that their voltage magnitudes for each of the phase is same and their angles are differing from each other by 120 degrees. So, the internal buses are the balanced buses, but the original buses, that is bus 1, 2, 3, 4 are unbalanced bus. Right. So, then what we have basically managed, essentially discussed, that if I have got an n bus system in which if there are m generators, n bus system having m generators, that I must write. So, an n bus system having m generators is augmented to an n plus m bus system because of the consideration of generator internal bus for every generator, right. And we also write that original n buses are unbalanced buses, bus 1, 2, 3, 4 are unbalanced, and internal m, that is bus 5 and 6 are the generator internal bus, they are balanced, correct. So, now with this, now we are ready to discuss that what would be the final list of the unknown quantities in this system. Then we will discuss that what are the known quantities in this system, and then in the third phase we will discuss that what are the equations connecting these known quantities to the unknown quantities of this system, and then lastly, which would be a little long discussion, that how to solve those equations to find out the unknown quantities, right. So, all these aspects we will take up one by one gradually starting from the next class. Thank you.